everybody, my name is Josh. I was a computer science examiner for multiple exam boards, head of computer science in UK based schools, and now I run a tutoring business where I've helped thousands of students to get better grades in computing related courses. And what I'm trying to do is put together a series of lessons where you can watch them and you can get the key bits of information so that you've got talking points about everything in the exams, and then you can get those top grades. Now, I've been going through with my students all to do with different data structures. So what I thought I'd do is I'd just go through each data structure. We've already done stacks, queues, and hash tables. So if you haven't seen those videos, go onto those because they are going to help you massively. And we're going to be looking at graphs today, which is relevant for all specifications. Now, with a graph, if it just asks you to describe what a graph is, what it's made up of is vertices or nodes. We're going to have a look at what that means in a second. And it's also got edges or arcs. They're just different words for the same thing. So vertices and nodes you can use interchangeably. Edges and arcs also. These are used to represent relationships, and this can be used in things like a sat nav when you're trying to work out how long it's going to take you to get to a particular place and the different routes you can take. They can also have different features about where they can be undirected, directed, weighted or unweighted, and we're going to have a look at all of these different examples and what they actually mean. Now, some of the uses, as we've already said, sat navs. Artificial intelligence, Cambridge International, I'm going to do a little bit more of a in-depth lesson on how graphs are used in AI, but this is just a general just a basics on graphs to start off with. Also used with machine learning, very important with AI, networking, web page rankings. There's plenty more, but there's just a few examples that you can use. Now, we'll have a look at this picture. So you've got the nodes / vertices here. We've got the edge. We've got the weight of how long it's going to take to get from one place to another in this particular case of where you're going from Bolton to Bury, and this is just what you're looking for. Now, a more complex question of what they're going to do is get you to try and represent the data in what's called an adjacency matrix. Now, this one isn't finished, and I'm just going to show you how to finish this off. Okay, so this is a directed, but it's unweighted. The only difference is let's say that there was a 6 going from D to A. Okay, so D to A. All we'll do is instead of putting a 1 there, we just put a 6 there. Okay, that's the only difference when it's weighted and unweighted. So as you can see, I've been going through D to A, D to A, not A to D. Okay, so D to A, so the 1 goes there. Mistake which people are going to make is they're going to put that up there. Do not do that. If it's a directed one like this. And then we've just gone through the rest of them. And one of the other ones that we've got here is we need to have a look at C to F, because as you can see, C to F. So all I'm going to do, C to F, put 1 in here. The other one that we've got as well is D to F. So D to F. So we put a 1 there. And that is a completed version of this particular directed graph here. Now, as I said, this is what it would look like if it was an undirected weighted graph where you've got numbers on there. And essentially what the computer is going to be doing is it's going to be calculating if you needed to get between a particular, so let's say A and D are different locations. What it might be doing is it's going to suggest the shortest route, and the smaller that number is, that's the more likely it is to suggest that one, unless there's going to be particular traffic and things like that on there. So the thing with this one being undirected though is that, as you can see, we have to put it in both locations. So if we take C as an example here, the 7 so between A is going to go there, but we also have to put it in up here because A to C. So it's essentially we have to double up all of the information in there. So that's why you've got 2 values there, because it's undirected. Now, to finish this one off, where we have got just a couple of values left, is I left the C here, so the 10, so C to F, 10. But we have to also remember to put it over here as well. And then the other value that I missed out there was also going to be the D to F, so that's going to be 6, so D to F, 6, but also just remembering to put it over here as well. And that is now the completed adjacency matrix. What are the advantages and disadvantages of adjacency matrices? The key thing is it's convenient to work with, and adding an edge is really, really simple. The disadvantage though is if it's quite a sparse graph, which just means it doesn't have many connections on there, we can actually waste a lot of memory by doing that. And we're going to have a look at another example now, which is the adjacency list. This is an alternative way of representing the data. And if you were to get a question on this, so if we look at this one, which is going to be a directed but unweighted graph, you'll see how we represent it in there. So what we've got is we've got the A, and it's going to C. So that's why A going to node C. Now we don't have, so for example, the D going to the A, that's why I don't have the D in there. So if we go to D, you can see that A is in there, and that's how I know where those values are going to go. If it is a weighted graph though, what we need to do is we just also need to put the weight of it so that that's in there as well. So A going to C, this is going, so we're going to put the C and then the colon 7, so like a pairing of the two of them. And then also, because this is a undirected graph, we're now going to put the D and the 13 in there. So that's how it's different from this one, because this one's directed, this one is not directed. And then if you look at the values for D here, we've also got the A13 in there as well. So we've got to put both of them in there. Okay, so the last thing to go over is just the advantages of using adjacency lists. The main thing is that we kind of covered in the weaknesses of the adjacency matrices is it's so much better and so much more space efficient than the adjacency matrices. So if we haven't got as many values, this is going to be the one that you're going to be using. So if it's a sparsely connected graph and it's big, this is going to be the one that you're going to go for.